Hello and welcome to yet another review session from CDLI to help you prepare for your final examination in Calculus 3208. I hope your studying is going well, and today we're going to talk about a very specific topic here and a very important one, probably the most important thing in the course actually. We're going to talk about slope of a tangent line and how do we find that exactly compared to approximately like we've seen before, and that's something that we call the derivative at a point for a particular function. All right, so this is a heavy topic, so we've got some work to do here. So the first thing we're going to realize is that we're going to have a couple of different definitions for this thing we call the derivative, and we'll see how one of them is a more commonly used one. But we'll have a first and a second definition for the derivative that we can take a look at, and then we're going to talk about how do we find the derivative, which we call f prime, at a point x equals a. So all those details will become clear in time. Okay, so let's get started by looking at the graph of a function f of x, and let's say we wanted to find the instantaneous rate of change or the instantaneous slope of that particular function at a very specific point. And the point we're going to have here is P, which has coordinates of a for x and then f of a as your y coordinate. So what I'm going to do is I'm going to draw basically what a tangent line would look like on there. So it looks roughly like that on the first diagram that we have. So let's just label a few little facts about this stuff to help us get situated a little bit. So we start with P here, and let's remember how we would find an estimate for the instantaneous rate of change. What we did before was we chose another point Q, like this one, that should be relatively close to. Now this one's a little bit far away probably, but it's spaced out a little bit for the purposes of illustration. But we choose another point Q that has its own x and y coordinates, and we're going to use that point to help us estimate the slope of the tangent. So basically we call this line that goes from P to Q is our secant line here. So that secant line that we have here in blue, we'd find the slope of that and say that that was a relatively good estimate for the slope of our tangent line that we have. And again, this one's exaggerated a little bit. So let's look at the coordinates of some of these points in terms of our axes here. So at this point right here at P, our x coordinate is at A, and then Q is a certain distance away, and so we're going to say that the x coordinate at Q could be anything we choose at all x. So we'll just call that x for now, and we can see on the x-axis that its point would be over here. So if we want to think about the change in x to find the slope of the secant line, it would be x subtract a right there. Okay, then if we think about a change in y for our y coordinates, it would be the height that we have right for this point. So somewhere over here on the y-axis would be at that height, and that's for q, and then the height for p would be down here. So those heights are the y coordinates given by f of x and f of a, and so that change in y would be given by f of x minus f of a. So what we're going to do with that is we're just going to write a little slope formula here. So we would say the slope of our tangent, so I'm just going to call that m tan, would be about equal to, so this is how we estimated before. In this case, we're going to use the function notation to write it out. So we could have f of x minus f of a, all divided by x minus a, like so. Okay, so what we think about now is we don't want just an estimate anymore. We want to really figure out what is the exact slope of this tangent line that we drew right here. So we're going to have to find a way to figure that out. So what we do is we don't think about it exactly first. We just think about improving our estimate a little bit. So if you look at the second diagram that we have over here, the first case, what we've got is this line T that's given as the actual tangent line. And all those other lines that are drawn on the curve, those are secant lines. And this is the first one that we've drawn, the line that goes from P to Q, if we put Q way down here. And you can see that the slope of the actual tangent and the slope of this secant are really nothing alike at all. But we want to improve our estimate, and this is the real basic premise here. To improve your estimate, you just move the point Q that you chose from this one to a point that's closer. And when that happens, we can see that the slope of our secant line now is actually closer to the slope of the tangent line. And if we move it even closer, we'll improve our estimate again. How close could we put it? Well, if we knew what the function f of x was, we could choose any value of x that was arbitrarily close to the point P. So, and the closer we get to that, then the closer we would get to having the true value. And this should start to look a little bit like some of the concepts in a previous unit. We could find the actual slope of the tangent if we think about using this as our estimate, but looking at what happens and predicting a value of what would happen by using a limit as we let the value of x, which is of course the x-coordinate at the point Q, get really close to the value of a, which is the x-coordinate at the point P. And the limiting value of this little fraction that we wrote down would actually, if we can find its limit, which hopefully we'll be able to do, will give us the exact value of the slope of that secant line. So that's the ideas behind what we're after here. So that's spelled out in a little more detail for you here. I'll just run through this quickly because it's kind of the same things that we talked about. But we're going to start by finding the slope of a secant, just like we set it up. So we've got the y-coordinate at Q minus the y-coordinate P, etc., which ends up looking like f of x minus f of a over x minus a. Okay, so we're going to then try to improve our estimates by making Q a point that gets closer and closer to P. And when that happens, or we can make that happen by allowing the x-coordinate of Q to get really close to the x-coordinate of P, so we say that x approaches a, which then forces f of x to get close to f of a. So then the slope of the tangent, and this is actually a definition if you want to look at it that way, one of the two definitions we're going to have, this is what we call the derivative. So one of the two most important words in calculus that you can find is derivative. The other one is integral, but we'll get to that at a later time. So what we do is we take that limit that we just talked about, and that'll give us the exact value of the slope of the tangent. So that's the idea behind a derivative. It's just a way to get the exact value of a slope of a tangent. Well, we have some funny ways to talk about it, though, because in the language of calculus and in the notation of calculus, the derivative wears many hats. Sometimes we call it the instantaneous rate of change. Sometimes we call it the slope of the tangent. Sometimes we can write it out this way, sort of as the limit of our slope formula, as the two values of x get really close together. And if that's the case, another way to say that would be the limit of our slope formula written with the delta y over delta x business as delta x approaches 0 there. And when we think about delta y over delta x being the slope of a secant, because there's some change in y and some change in x, as we let the change in x get really small, infinitesimally small we say, we then call that a differential, and we call it dx. And the corresponding differential for y that's tied directly to that, we call dy. So one of the more common notations we use to represent a derivative is this dy over dx. Okay? So let's get down to business. Now we're going to look at a second definition of a derivative. So another way to figure out the instantaneous slope or the slope of a tangent line exactly. So let's look at this crazy business we have set up here. So again, this T line that we have is the tangent. And so what we do is we arbitrarily choose some point Q over here, and we want to make it fairly close to P, and then we could use this secant line that we create with that to give us an estimate for the slope of the tangent. We don't label Q this time as x and f of x though. What we do is we say that horizontally, across the x-axis here, so horizontally, we say that we choose point Q to be a distance h, and in this case it's to the right of the point A that we had. So if that distance h is how far we are away across the x-axis, then the x-coordinate for Q becomes A plus that distance h. So we write that right in there. A plus h is our x-coordinate, and then of course the y-coordinate is just the value of the function at A plus h. So it's f of A plus h. So then our change in x and change in y will be found by saying change in x will just be h, or A plus h minus A, which is just h. And then our change in y will be this monster, f of A plus h, which is the height here for Q, minus f of A, which is the height right over here, that height along the graph there for P. So it's that height. So then if we write those two together to make our slope formula, it looks like what we have over here on the left, f of A plus h minus f of A, all over that business, which we quickly simplify to look like this. That is what mathematicians refer to as the difference quotient. We call it a difference quotient, or it's really just a slope formula, but we call it a difference quotient because we're finding the difference between the two y coordinates, and we're dividing it by this value h that's going to shrink on us, and we call that difference. So subtraction makes a difference, and then divide makes a quotient. So it's a difference quotient. Then in a similar fashion to what we did before, we think of p. To improve our estimate, we want to get q getting closer to it. So we're going to move q closer down our curve, and as that happens, we're going to make all that happen by controlling the value of h that we choose. So we can choose smaller and smaller values of h, which forces q down the curve, gets it closer to p. So we take a limit of this difference quotient that we had, and we get this stuff. And it ends up looking just like that. And another notation now, yes, another notation that we have for this thing we call the derivative. Instead of saying dy over dx or any of that other stuff, we call it f prime of a, as it's written right there. So this is not an apostrophe, it's just like f with a little tick mark there. So it's called f prime, meaning it's now the derivative of the original function. Okay, let's move on to some concrete examples and see if we can make any sense out of this. So the first one says find the derivative of that function at the point where x equals 2, and it's already preset for us to use both methods that we saw, so both of our definitions. So the first one, we're going to end up getting our f prime of 2, if you want to call it that, or you can call it dy over dx when x equals 2. And in that case, we want to take the limit as, and remember the formula said as x approaches a, of f of x minus f of a, all over x minus a. So we fill in the details for that one, and that's going to be the limit as x approaches a of f of x is x squared minus 5x plus 9, and then we're going to subtract the value of the function at a, and then in the denominator we're going to have x subtract just the value of a, which we know is 2. So the only thing we don't have is this number right here, which is the value of the function at x equals 2. So we're going to say this is the limit now as x approaches 2, not a, excuse me. So when x equals 2, we're going to have 4 minus 10, so it's negative 6, plus 9 is a positive 3. So that function value right there is a 3. So now we have the limit as x approaches 2 of x squared minus 5x minus 6 all over x minus 2. And if we try to fill in for direct substitution of our limit here, we'll find that we get a 0 over 0, which is one of our indeterminate forms. So what we do instead is we factor the numerator using one of our limit strategies that we've learned previously. And that factors to give us x minus 6 times x plus 1 Oh, and if you'll excuse me, I've just spotted a little error here. This said 9 minus 3 used to be positive 6, or at least it was when I went to school, so I'd better fix that. And that will, of course, change the factors that we have down here. So excuse me for that. I'll just fix that real quick. Get that old business out of the way, and then we'll make it look a little nicer. Okay, so in this case, it's going to be x minus 2 times x minus 3. There we go. That's better. And that's all over x minus 2. And we still have the limit as x is approaching 2 here, but we can eliminate those two factors, fill in our 2, and we'll just get 2 minus 3, which is negative 1 for the slope of our tangent, or the value of our derivative. So if I were to draw a tangent line that touched that curve at the point where x equals 2, that line would have a slope of exactly negative 1. Neato. All right, so now let's find f prime of 2 this time by using our other definition. So the other definition says if we're trying to find f prime of a, sorry, we'll write it that way first, f prime of a is going to be equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And of course, in this particular example, a is just the value of x that we've chosen, so that's going to be f prime at 2 here. So f prime at 2 will be the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. So we already worked out the f of 2 business in the previous method when we did that. So the f of 2, we know this part right here already is going to be working out to 3. To get f of 2 plus h, I have to take my function f of x, and like we learned a long time ago, we've got to fill in 2 plus h everywhere we see an x there. So that'll be 2 plus h squared minus 5 by 2 plus h. And then plus 9, and then subtract our f of 2, which we already evaluated over here, to be a 3. And then that's all divided by h. Okie dokie. So when I work this out now, I've got the limit as h approaches 0 of 2 plus h squared is going to be h squared plus 4h plus 4. And then I've got minus 5 times 2 is 10, and 5 times h is minus 5h. And then plus what we have on the end here is 6, all over h. And then we'll collect like terms, at least in our numerator to start. So we have the limit as h approaches 0. And up top we're going to have h squared minus h. And then 4, negative 10, and 6 all add up to 0. So we just got h squared minus h all over h. So I can remove an h as a common factor of my numerator. So I have the limit as h approaches 0 of h outside of h minus 1 all over h. Seeing that those two will cancel out, and then the direct substitution of 0 for h will give us 0 minus 1, which gives us a slope of negative 1. It's exactly what we got when we used the other method, and exactly what we could have predicted. Okay, so two different ways to approach defining a derivative and using that definition to find the instantaneous rate of change. So look at this second example. It says use the first definition, okay, to find dy over dx, and we've got an interesting notation here. Dy over dx, and then this vertical bar with x equals 3 there. So what that means is just find the value of the derivative, or that slope, of the tangent at exactly x equals 3. Okay, so that's going to be the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. So in this case, that will be the limit as x approaches 3 of the square root of, it says x plus 5, minus the square root of 3 plus 5, which is going to be the square root of 8, all over x minus 3. There we go. Okay, so now we have to evaluate this limit, which is also indeterminate, 0 over 0. So what we can do to evaluate that is, it's a limit with radicals. So remembering our strategy for that business, we multiply the numerator and our denominator by the conjugate of the thing that's giving us a bit of a headache. Notice I didn't simplify the square root of 8. I don't really care about the fact that that's not simplified yet. If I get an answer in the end that I have to simplify, I will. So the conjugate of that, I change the I've got x plus 5 plus root 8. And if you remember back to our limit strategies for that stuff, we do the multiplication to figure out what the conjugates multiplied together will give us. Remembering that when we multiply two conjugates, the middle terms always cancel out. So what we end up with is this first term that we have here squared, so that's just x plus 5. And then subtract the last term squared, which turns out to be just 8. And that's all divided by x minus 3 times that ugly conjugate, square root x plus 5 plus the square root of 8. Alrighty, so that's now going to tell us that since our numerator is going to be the limit as x approaches 3, and our numerator is x minus 3, and our denominator has an x minus 3 factor in it, then we're going to be in good shape, we think, to help us evaluate this limit. So when we put this stuff together, they're going to cancel out, and then we can just fill in our 3 to get a value. So this will give us 1 over the square root of 3 plus 5, which is 8, plus another square root 8. So this is going to be 1 over 2 root 8, and we don't like to have that, so we'll rationalize. So multiplying by root 8 over root 8 will give us root 8 over 16. And root 8 is just 2 root 2 over 16. So we have square root 2 over 8. And that is our final value for the derivative of that function at that value. Okay. So let's roll on and look at what's next here. So we've got another example. This time we've got a rational function that we have to try to find the derivative of. So let's see if we can manage this one. So we're going to take limit and difference quotient definition. So that's the second one. So we've got f prime of, in this case, 1. So that's going to be the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Alrighty, so f of 1 plus h, I've got to take my function I have up there, and in its equation I have to change the x's to 1 plus h. So it's 2 outside of 1 plus h plus 3 all over 1 plus h plus 1. And that's going to be subtract f of 1, which is going to be 2 times 1 is 2, plus 3 is 5 up top, and 1 and 1 are 2 in the bottom, and that's all divided by h. So let's simplify the first fraction that we have there, and we'll have the limit as h approaches 0 of 2 plus 2h plus 3 all over h plus 2 minus 5 over 2 all over h. So I have to add my fractions together in my numerator there, and when I do that, I'm going to get, let's see, I got a common denominator of 2 outside of h plus 2. So this will be the limit as h approaches 0 of 2h plus 5 multiplied by 2 over 2 times h plus 2, and then subtract 5 times h plus 2 over 2 by h plus 2. And all that's still divided by h. So we can put this stuff together now and have the limit as h approaches 0 of 4h plus 10 over, subtract 5h, and we're going to subtract both terms here. So minus 5 times 2 is 10, and that's all over 2 outside of h plus 2. And instead of dividing by h now, I'm just going to multiply the whole thing by 1 over h. Make it a little simpler. So then our numerator will simplify. We'll have the limit as h approaches 0. 4h minus 5h is negative h over 2 outside of h plus 2. And that's multiplied by 1 over h. Those h's can get destroyed. And then I fill in the 0 this time. We're no longer indeterminate. We get negative 1 on the top. And 2 times 2 on the bottom is 4. So minus 1/4 is the value of our limit, and therefore the value of the derivative for this function. Alrighty, let's see what's next. Whew, another one. So this time it says use the definition of the derivative to find dy over dx at x equals 2 for the function y equals the square root of x plus 4. Sorry, the square root of 3x plus 4. So let's use our second definition, because we did one like that already with the first definition. So we'll say dy over dx, where x equals 2. And this is the more common definition that we use anyway. So we're going to say the limit as h approaches 0 of f of x plus h. So in this case, that's going to be the square root of 3 times 2 plus h plus over minus our f of 2 in this case is going to be the square root of 3 times 2 plus 4. And that's all over h. So a quick simplification in my numerator, I have the limit as h approaches 0 of the square root of 6 plus 2h plus 4 minus the square root of 6 and 4 are 10. And that's all over h. So in this case, I have the limit as h approaches 0, 2h plus 10 square rooted. Oof, that 10 got pretty messy. Minus the square root of 10 all over h. And so we're going to multiply by our conjugate here, which is the square root of 2h plus 10 plus the square root of 10, all divided by, same thing, square root 2h plus 10 plus the square root of 10. Okay, so when we work all that out, we have the limit as h approaches 0 of, in the numerator, we're just going to have 2h plus 10 minus 10. And in the denominator, we'll have h times 2h plus 10 square rooted, and then plus the square root of 10. And so we put all that stuff together, and it's going to give us the limit as h approaches 0 of 2h over h times all that crazy radical stuff again, 2h plus 10 plus the square root of 10. And canceling out the h's, we can now fill in the 0 and see what this works out to be for us. So let's take it up here, and we'll say that this is the limit as, we'll fill in the 0, so we don't need our limit anymore. This will be equal to 2 divided by 2 times 0 plus the square root of 10 is just the square root of 10 plus another square root of 10. So this will be 2 over 2 root 10, which is 1 over square root 10, which when rationalized gives us root 10 over 10. Okay, and then we've got our value of our function taken care of, the value of our derivative, sorry. Okay, so here's the OR turn question. You can pause your video and have a look through that and see what you can come up with this one. And then there's the solution worked out for you. And here are some key ideas from this section. So let's have a look at those for a sec. So to find the instantaneous rate of change, we want to find the slope of the tangent. And the first definition of the derivative, we use this formula, and for the second definition we use this one. 99% of the time though, if you're ever asked a question and you want to use, unless they specify, they just say use the definition of the derivative. This is the formula that we're after, this one down here. That's the big one. Okay? Alrighty, thanks very much. Hope that helps. Good luck studying.